Okay, before we start, I'd like to give you 3 seconds to guess how tall I am. Go. Why, I'm 9.3. What, 9.3 bananas tall? What do you mean? Of course it's a valid... A centi what? Hi, I'm Thyme, and let's learn about units and measurements. First of all, I want to say that I am actually 9.3 bananas tall, or roughly 176 centimeters, or 1.76 meters. These number-letter pairs are what we call physical quantities, and they're all valid measurements of height. So what is a measurement? People throw that word around, but what does it mean really? In science, a measurement is quantitative data that describes a property of an object or an event. Properties like how tall I am, how fast an object is going, how bright a light source is, and how many subscribers you have. You need numbers to describe them, and without numbers, you're stuck with trying to explain how you're taller than something else without knowing or being able to tell exactly how tall you are by comparison. Back to my height. Here, you can see that all measurements are made up of the number or magnitude and the letters or unit. The magnitude is used to describe the size of the property relative to the unit. In this case, my height is 176 times the height of 1 centimeter. If I were to only say that I'm 176 tall, you'd still have no idea how tall I am because you have nothing to compare it to. The magnitude doesn't really mean anything on their own, so that's what a unit is for. But how do you decide what unit to use? Well, that's up to you, as long as everyone using the measurement agrees to use it and stays consistent with it. If your group of friends each have an idea of how much your favorite can of beans weigh, feel free to use that as your go-to unit for every time you or your friends mention something's mass. That way, when you say something weighs 10 or 10 cans, you guys have a rough idea of how much it weighs. Unfortunately, the instant you say the same thing to a stranger, they won't know how heavy that is, since they're not familiar with the unit you're using. That's what standard units are for. Instead of can of beans, it's always safer to use a unit that you know most people are familiar with. In the case of mass, its standard unit would be the kilogram. Everyone knows what a kilogram is, and when you say something weighs 10 kilograms, they would most likely have an idea of how heavy it is. Standard units also tend to have their own symbols, so instead of writing kilogram, you can just write a shorter, friendlier kg, and people will still know what you mean. Nearly every kind of measurement has a standard unit. Everyone measures time in seconds, temperature in Celsius, length in meters, and so on. Well, almost everyone. In the US, for instance, people measure mass in pounds and length in feet. These are called imperial units, and they were established by the British Empire, hence imperial. They're based on units people have been using since the Middle Ages, and weren't formalized by the British until around the 1800s, when they still had a lot of the globe colonialized. On the other hand, if you're using kilograms and meters, you're using metric units. These units came about in France in the late 1700s, right before the imperial system was established. Unlike the imperial system, it was more based on an attempt to reinvent units instead of simply formalizing ones that came before. At one point, it was even proposed to Britain and the US, but rejected because of disagreements in unit definitions. So Britain and the US decided to stick with the later formalized imperial system. Meanwhile, France kept developing the metric system, and it ended up spreading and gaining popularity anyway, mostly due to trade. So you have two major sets of standard units that were made at about the same time and for about the same reason, to make it easier for everyone to communicate measurements. There have been dozens of others before this, but they weren't as popular. Although 2 is better than dozens, it's still not ideal when you're sharing calculations with the whole world, especially as technology booms and people start collaborating internationally. Since everyone wants to be on the same page, people have started leaning towards the metric system. Even the UK, post-British Empire, began metrification in the mid-1900s, to varying degrees of success of course. Those of you who are British, feel free to comment down below. Meanwhile, the US seems to still be okay with measuring mass in pounds. It's not that they don't feel the need to change at all, it's that they're so used to using imperial at this point that suddenly changing to something else is a literal culture shock. It's like asking someone to change languages. It's a slow and frustrating process. Today, only 3 countries in the world officially use the imperial system, and the rest use a modernized metric system called the SI, or the International Standard of Units. Here's a more complete comparison of units used in both systems. But wait, what's this? They're using different units to measure the same thing, even though it's one standard? Yep, there's really nothing wrong with that. Like I said, as long as everyone agrees and is consistent with it. Why, you ask? Well, like everything about units so far, it's to make things clear and easy. Let's take an example. In metric, people measure mass in grams, or G, as well as kilograms, or kg. A kilogram is 1000 grams, but instead of saying or writing that, you can just say 1 kilogram. A gram is also 1000 milligrams, a million micrograms, and so on. These bits we add to the front are called prefixes, and in metric, we typically use them to describe units in powers of 10 or 1000. Here are the most common prefixes. In some cases, we don't use a prefix, but another word entirely. A ton is 1000 kilograms. Alternatively, it's also a megagram. The prefix mega meaning million, so million grams, but no one really says that. In math, people generally don't use prefixes, instead use powers of 10 like this. This makes it easier to see and compute in complex expressions and equations. Anyway, these are all the same thing, they're just preferable to use in different contexts. A spice trader would use milligrams to quantify their superlight products, instead of having to use kilograms and then having to write or say all the zeros that come along with it. Meanwhile, the imperial system doesn't have prefixes. Length can be measured in feet, but there isn't really a kilofoot. Instead, you have the following. An inch is a 1/12 of a foot. A yard is 3 feet, and a mile is 5,280 feet. There are other units for length as well, along with other measurements like mass and volume. You can see that it's a bit inconsistent. This is because the imperial system is based on older units that didn't pay much attention to how they relate to each other back at the time. It can get pretty inconvenient to compute and convert units, especially if you use units derived from metric that don't really have an imperial equivalent. This is why most scientists, engineers, and occupations that use a lot of math prefer to stick to SI units whenever it counts, even though they live in a country that uses mostly imperial. So, for the sake of science, we'll be using SI since it's the de facto scientific standard. Speaking of derived units, a derived unit is a unit that results from a combination of base units. There are only 7 base units in SI: length, mass, time, temperature, electric current, luminous intensity, and amount of substance. Every other unit is derived because they're always a combination of one or more of these 7. For example, volume is just a combination of 3 lengths. Speed is a combination of length and time. That's why if you want to see the relationship between your physical quantities, you can include their base units in your calculation and combine or cross them out accordingly. This is called dimensional analysis, where each base unit may be written as a dimension, and you need to follow the following rules. 1. You can only equate physical quantities with the same dimensions. So if dimensions on the left of an equation combine to make meters per second squared, then the right has to be meters per second squared. Otherwise, you're missing something along the way. 2. You can only add physical quantities when they have the same dimensions. You can't add a driver's mass with his car's speed. If you're adding 10 things together and one is in kg, the other 9 needs to be in kg. 3. You can multiply physical quantities together and their dimensions are multiplied alongside them. Note that dividing is just multiplying to the power of -1. So, multiplying someone's mass and speed results in a physical quantity with a unit of kilogram meters per second. This analysis makes it abundantly clear that combined units are really just multiplications or divisions of singular, more basic units with their own magnitude each. When you write 10 meters a second squared, you're really just writing a shorter version of the fraction 10 meters over 1 second times 1 second. You might also see different units used in place of a combination of base units. For example, the unit for force is newtons, but what it really is just kilogram meters over second squared. Likewise, the unit for frequency is hertz, which is 1 over second, or second to the power of -1. Using these alternative units makes it shorter and more noticeable in context. Be wary though, some symbols can mean different units, and some units can have different symbols or represent different things. By the way, almost all units that are named after people start with a capital letter. Okay, back to base units. Did you know that until very recently, the kilogram was based off a small platinum cylinder kept in a vault in France? It's called the International Prototype of the Kilogram, or IPK, and it's the very definition of a kilogram. Everything in the world that is exactly the same mass as this artifact is, by definition, 1 kilogram. This happened often with units back in the day. They used existing, usually already commonly used objects as units, then tried to keep them as uniform as possible. Or in this case, they created one and tried to maintain its unit intended property, the mass, as fixed as possible. But over time, they found out that because of routine cleaning and exposure to air, it was estimated to have lost about 50 micrograms. And we can't have a standard that's constantly changing. So, what did they do? They redefined the kilogram in terms of something that doesn't change that much, if at all, a universal constant. In this case, something called the Planck constant. Now, we'll save the details for another time, but as of the moment of this recording, all the base units are based on phenomena with a fixed property, like the speed of light, frequency of a cesium atom, and the Avogadro number. I suggest you look up the definitions of these base units along with how they've evolved over time too, it's pretty interesting. Anyway, I think that just about covers it for now. Half of it. For the other half, be sure to watch the second part in my channel, or just click the link down below. We'll be talking about how writing zeros can screw you over, how wrong your measurements are, and how to live with your own mistakes. Thank you so much for watching. I hope it's been helpful. Please like the video if you like it, dislike the video if you don't. Feel free to share or leave a comment if you'd like to add anything or if I got anything wrong. Do subscribe if you want to see more content like this. Have a nice day and see you next time.